Okay, we finally have arrived at the fundamental theorem of calculus, and so on your worksheet you'll see that it comes in two parts. And so the fundamental theorem of calculus part 1, on your sheet it says if f is continuous on the closed interval from a to b, then the function g defined by g of x is the integral from a to x of f of t dt from a is less than or equal to x is less than or equal to b, is continuous on a to b and differentiable on the open interval from a to b, then g prime of x equals f of x. Here is the big deal. G prime of x equals to f of x. What they have done in part 1 is established that connection between a derivative and an integral. This is huge. This is what ties both of the branches of calculus together. It's a really big deal. So it gives a precise inverse relationship between the derivative and integral. We need to appreciate that because it also saves us a lot of work. So in words, this is what part 1 says. The derivative of the definite integral with respect to its upper limit is the integrand evaluated at its upper limit. That's what it says in words. But its meaning is big. It means that integration is related to the derivative. Now, part 2 says this. This is the definite integral where they define this. It says the integral from a to b of f of x dx is equal to the antiderivative is evaluated at the upper limit minus the antiderivative evaluated at the lower limit. That is huge because that means we get to just plug in numbers and do a subtraction, and whatever value we get, that's the area under the curve. Why does that help? It helps immensely because it means that we do not have to, we no longer have to do rectangles and do an infinite sum of rectangles to try to figure this out. It's a huge help. And so who do we give credit to for figuring all this out? Isaac Barrow is a fella that he discovered that the tangent problem that we looked at when we're looking at the limit as h goes to 0 of the difference quotient, as we get closer and closer and closer, the limit of the slope of a tangent line as opposed to the slope of a secant line, he realized that the derivative problem was very, very closely related to the area problem. So he's the one who kind of formed a connection. But it was Isaac Newton and Leibniz who did a lot of modeling and developed it into a mathematical process that we get to use. And they used it so that enough and wrote it in textbooks and wrote the formulas down so that we could use this. So it establishes the connection, and why is it so helpful? We can compute areas very easily without having to do all those infinite limits and stuff. So big deal. We appreciate all of their good work because now we get to use it. Let's go ahead and use it. We got a few examples here. Number 1, sketch the region enclosed by the given curves and calculate its area. So number 1 is this. Y is equal to the square root of x, and they want us to calculate the area enclosed by this curve and this curve. Y is 0, which this is just a horizontal line, otherwise known as the x-axis, and this line, x is 4, which is a vertical line. So let's sketch the sky. The square root of x is a curve that looks like this, basically. And you can plug in some numbers, you can put in some x values to get this graph. Y equals to 0 is the x-axis here. This is the x-axis. This is y equals to 0. So it's enclosed by this, and then x is 4. So here's 1, 2, 3, x is 4. We'll go up here. And so this area is what we're interested in calculating. Okay, how can we do that? Let's use an integral. Okay, let's integrate from 0 to 4 square root of x dx. So let's do this. We already know how to integrate because we practiced 5.4, 5.5, 4.9. Those were antiderivatives. What could give us, whose derivative would give us this? I'm going to rewrite this first into x to the 1/2 and use the power rule. This becomes x to the 1/2 plus 1. or 3/2, divided by 3/2, which is the same thing as 2/3. And we're going to evaluate this between 0 and 4. So this is 2/3 times 4 to the 3/2 minus 2/3 times 0 to the 3/2. All right, 0 to the anything is 0. 0 times anything is 0 minus a big old 0 right here is what happens here. All right, I'm going to rewrite this back into radical form. This is 2/3 times the square root of 4 to the 3rd power. Remember, a to the m over n is the nth root of a to the m. So I'm converting this back. The radical and this power right here, those, remember order of operations, please excuse my dear Aunt Sally, P is power. This is a power, and this is a power. This is a fraction power, and this is a power. Those tie. They have a tie for who to do first. So you can do either one first. I'm going to choose to do the square root of 4 first. So this is 2/3. The square root of 4 is 2, and then I'm going to cube it. So 2 cubed is 8. This is 2 over 3 times 8. This is going to be 16 over 3. That's the area under this curve between 0 and 4. Let's do number 2. The second one says y is equal to 2x minus x squared, and it's bound by y is 0, which again is the x-axis. So let's look at this guy. This is a parabola. So let me just see where the x-intercepts are, the zeros. 2x minus x squared. Where are the zeros? I'm going to factor out x. 2 minus x. Let's see. 2x minus x. Okay. So the x-intercepts are at x is 0 and at x is 2. X is 0 and x is 1 and this is 2. And so we know this is a parabola. You could do some other things to find where the vertex is, negative b over 2a, and you'll find that it's at 1. If you plug in 1, 2 minus 1, it's at 1. So this is our vertex at 1, 1. All right, and so this is what our parabola looks like. And so what they want is this area under the curve right there. So to do this, let's integrate from 0, from x is 0 to x is 2 of this curve, 2x minus x squared dx. So this is very easily the power rule. This is 2x squared over 2 minus x cubed over 3 evaluated from 0 to 2. 2 divided by 2 is 1. So this is just x squared minus 1/3 x cubed. So let's plug in the 2. 2 squared is 4. 2 cubed is 8 minus 8/3 minus 0 squared minus 1/3 0 cubed. And so this is a big 0 again. So basically we have 4 minus 8/3. If I get this common denominator of 3, then I've got 12 minus 8, or 4/3 is the area under that curve. So that's how you can convert that to an integral and do it very simply. So thank you, all of those smart guys who lived a long time ago, for giving us that theorem. Let's look at the next one, and it gives us this curve. I have it printed on there. It says the boundaries of the shaded region are the y-axis, and the line y is 1, and the curve y is equal to the 4th root of x. Find the area of this region by writing x as a function of y and integrating with respect to y. We've never done this before. We've always integrated with respect to x. But remember when I said it wasn't dependent on x, you could do it with respect to whatever variable you want. So what we're going to do is kind of turn our head sideways and look at the y-axis. And this curve is bound by the y-axis here. So we're going to kind of look at it like that. Okay? We're going to integrate from 0 to 1 on the y-axis of this curve. But in order to do that, we have to rewrite x in terms of y. So here we go. Let's do that. So on your worksheet, we have this curve right here. We've got this curve right here, and it's bound like this, and it's kind of like this, right? And so this is 1, and this is 0, and this is y is 1, this curve, and we have y is the 4th root of x. So instead of integrating on the x-axis, we want to integrate up with respect to the y-axis, which you're allowed to do. So we want to integrate with respect to y from 0 to 1. But in order to do that, we don't want x's here, we want y, so just solve for x. Raise both sides of this equation to the 4th power. X is y to the 4th. And then we'll integrate. Let's integrate y to the 5th over 5 from 0 to 1. Plug in the 1/5 minus 0. The area under that curve is 1/5. And so that is a good thing to know how to do. All right, just a few more examples. Let's look at number 3. I'm just going to talk about this. It says the honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. And so they threw a derivative in there. So we know a derivative is a rate of change. It is the rate of increase of the bee population per week. So it says, what does 100 plus the integral from 0 to 15 n prime of t dt? What is 100 plus the integral from 0 to 15 n prime of t dt? What does this mean? All right. So if n prime of t is the rate at which the bee population is increasing, this is a rate of change. The antiderivative is not a rate, it's just an amount, right? So this, between 0 and 15, is the amount of bees that, the amount that the population grew in the first 15 weeks, and we add the initial 100. So this right here represents the bee population after 15 weeks. That's what that represents right there. Okay, let's look at the next one. If f of x is the slope of a trail at a distance of x miles from the start of the trail, what does this integral mean? The integral from 3 to 5 of f of x dx. What does this mean? Well, x represents miles, right? So what this is the change in elevation, the net change in elevation between miles 3 and 5. Because f of x is the slope of the trail, right? So this is just telling us, like, maybe between mile 3 and mile 5, right? Maybe if this is elevation, we went high and low and high and low and here. What would this give us? This would give us the highs plus the lows, and hopefully the trail did not look that steep, but it is the net change in elevation between miles 3 and 5. So you need to try to look at an antiderivative as not a rate of change, but kind of the whole change. Okay, so I'm going to break this video up and do the last 2 problems by themselves because sometimes they can take a little bit of time.